For decades, we were wrong about Europa, profoundly, almost embarrassingly wrong. We looked at this moon of Jupiter and saw a beautiful but ultimately unremarkable ball of ice drifting silently through the frozen darkness of the outer solar system. Scientists would mention it politely in conference talks, describe it as curious, and then quickly move on to more pressing topics. It was the quiet kid at the back of the classroom, present, noted, largely ignored. A frozen world at the edge of relevance. But something was happening beneath that flawless white shell. Something warm, something active, something that, by every intuitive rule we apply to dead, cold, distant worlds, simply should not exist. And for 2 decades, we pressed our faces against that frosted glass and could see almost nothing through it. That changed, not with a dramatic announcement, not with a rover touching down, or a drill breaking through ancient ice. It changed because a telescope, the most powerful infrared eye humanity has ever pointed at the sky, looked carefully, patiently, and told us things about Europa that rewrote our entire understanding of what this world might be. This is the story of what the James Webb Space Telescope found, and why it matters more than almost any discovery in the history of planetary science. Let's start with what we thought we knew, because that's always where the deepest cracks appear. Europa is one of the 4 Galilean moons of Jupiter, first observed by Galileo Galilei in January of 1610. Think about that for a moment. Over 400 years ago, a man pointed a primitive telescope at the night sky and watched a pinprick of light move night after night around Jupiter. He didn't know what he was looking at. He couldn't have imagined what we now know is down there. He just watched and recorded and wondered. He named this moon, along with its 3 siblings, and moved on. He was more interested in what these moons proved about the geometry of the solar system than in what they might harbor inside themselves. He had no reason to care about the interior of a distant ice ball. Neither did anyone else for the next 3.5 centuries. Europa is slightly smaller than our moon. Its diameter is approximately 3,100 kilometers. Compact, dense, almost perfectly spherical. If you held a model of Europa beside a model of Earth's moon at the same scale, you might have trouble telling them apart at first glance. The differences are in the details. The moon is gray, cratered, scarred by 4 billion years of asteroid bombardment. Europa is almost entirely smooth by comparison, one of the least cratered bodies in the solar system, which itself is a clue. A surface that stays smooth in a solar system full of impacting debris is a surface that is constantly being renewed. Something is erasing the craters from below. Its surface is almost entirely composed of water ice, and that ice is laced with reddish-brown streaks and ridges that stretch across the surface for over 1,000 kilometers. These are called lineae, fractures and pressure ridges carved by the constant gravitational kneading of Jupiter's enormous pull. They crisscross Europa's face like the veins on the back of an old hand, hinting at deep internal forces that never rest. And beneath that ice, beneath tens of kilometers of frozen water, there is an ocean. We suspected this since the late 1990s, when NASA's Galileo spacecraft detected subtle disruptions in Jupiter's magnetic field that could only be explained by a large body of electrically conductive liquid salt water. Not a thin film, not a trapped reservoir, a genuine global ocean, almost certainly containing more liquid water than all of Earth's oceans combined, sealed beneath an icy shell estimated to be between 10 and 30 kilometers thick. That ocean made Europa famous, because where there is liquid water, there is at least the possibility of life. Not a guarantee, not even a strong hint. Just a door left slightly ajar in a universe that usually keeps its doors bolted shut. For 20 years, that barely open door was almost everything we had. We couldn't see through the ice. We couldn't measure the composition of the water. We had no way to know what was dissolved in it, whether the chemistry happening down there was biologically interesting, or whether it was nothing more than cold, sterile salt water in eternal darkness. We were stuck outside, pressing our faces against frosted glass, unable to get in. The James Webb Space Telescope changed that calculation, not by drilling through the ice, not by landing a probe. It changed it through a method so elegant it seems almost deceptively simple. It stared at Europa's surface with exquisitely sensitive infrared instruments and read the chemical fingerprints of whatever was there. In September of 2023, 2 independent research teams published results from Webb's near-infrared spectrograph, NIR-SPEC, an instrument so precise it can identify molecules on a surface more than 600 million kilometers away. The chemical equivalent of reading the label on a bottle from across a city. Their target was a specific molecule, carbon dioxide. Now, CO2 by itself isn't particularly exciting. It's common throughout the solar system, found on Mars, in the atmospheres of Venus and Titan, in comets, in asteroid ejecta. The question wasn't whether it was there. The question was where it came from. Carbon dioxide on Europa's surface could have been delivered externally, by meteorite impacts, by bombardment with cosmic particles, by charged particles swept in on Jupiter's powerful magnetic field. That would be ordinary. That would be uninteresting. That would tell us nothing new about the ocean beneath. But there was another possibility. The CO2 could be rising from below. It could be seeping up through fractures in the ice, carried to the surface from the ocean itself. If that were true, it would mean something profound. The ocean contains dissolved carbon. And carbon, organic chemistry's central atom, the backbone of every form of life we have ever encountered, would be there, in the water, beneath the ice, in the dark. Both research teams found it, independently, using different analysis methods. They converged on the same answer. The carbon dioxide was concentrated not randomly across the surface, but specifically in a geologically young, chaotically disrupted region known as Terra Regio. This is a large area of disrupted terrain in the leading hemisphere of Europa, a place where geological models had long predicted that material from deep below should be periodically brought to the surface through a process called upwelling. The CO2 wasn't scattered like dust from an impact. It was dense, localized, concentrated exactly where you would expect to find it if it had been carried up from within. Geronimo Villanueva, a planetary scientist at NASA and lead author of one of the studies, was precise about the implications. The carbon dioxide is not coming from outside. Its distribution is entirely consistent with an internal origin. The subsurface ocean beneath Europa's ice contains dissolved carbon dioxide, and the geological activity in Terra Regio has brought traces of it to the surface, like a stain bleeding through fabric from below. Carbon in the subsurface ocean is not a luxury detail. It is a prerequisite. Carbon is the scaffolding of biology. Without it, the chemical reactions that could theoretically support life cannot take place. With it, the door swings open a little further. But Webb wasn't finished. In March of 2024, a separate research team used Webb to hunt for something even more dramatic: water vapor plumes. Jets of steam that might be erupting directly from Europa's surface into space. The Hubble Space Telescope had reported hints of such plumes in 2012 and again in 2016. But those detections lived on the edge of Hubble's sensitivity. Some scientists took them seriously. Many remained skeptical. The data was ambiguous in exactly the way that keeps researchers up at night. When Webb turned its instruments on the same region, the results were far more definitive, though not in the way you might expect. No large, sustained plumes were detected, no constant jets of ocean water spraying into space. At first glance, that sounds like a disappointment, but read it differently. What Webb actually showed is that Europa is not an Enceladus. Saturn's small, spectacular moon, which continuously erupts geysers from its south pole, fed by tidal forces that knead its interior like dough. Enceladus is a perpetual geyser machine, and we love it for that. NASA's Cassini spacecraft flew directly through Enceladus's plumes in 2008 and tasted their chemistry, detecting water, salts, organic compounds, and molecular hydrogen, the latter being a direct signature of hydrothermal activity. It was one of the most dramatic discoveries in the history of planetary science, and it happened almost by accident. Cassini was not designed to sample plume material. It just happened to be there. Europa's plumes, if they exist at all, appear to be more like occasional sighs than a constant shout. Intermittent. Triggered perhaps by specific orbital geometries. Moments in Europa's elliptical orbit when the tidal stress on a particular fracture in the ice reaches a threshold and briefly opens a crack, releasing pressurized water before refreezing. Like a pressure valve that triggers only under specific conditions. This means that Clipper, when it passes over Europa, will need to be in the right place at the right time to catch a plume in action. And its 50 flybys, spread over multiple years and multiple orbital configurations, maximize the probability of that happening. This matters for mission planning. Catching an active plume is a question of timing and luck. But the absence of constant eruptions doesn't diminish the ocean. It just means the ocean is more tightly contained, more patient, waiting to be reached. Now. Where does the energy come from? This is one of the most important questions in planetary science, and the answer is one of the most elegant pieces of physics in the entire solar system. Europa is very far from the Sun, at approximately 780 million kilometers, about 5 times Earth's distance. Sunlight arrives at roughly 1/25th the intensity we experience on Earth. The surface temperature sits around negative 160 degrees Celsius. By any solar heating logic, Europa should be frozen solid throughout, a dead, cold marble. But the Sun is not Europa's heat source. Jupiter is. Europa's orbit around Jupiter is not a perfect circle. It's a slightly elongated ellipse, and this shape is maintained by a complex gravitational tug-of-war between Jupiter and its neighboring large moons, particularly Io and Ganymede, which are locked with Europa in a 1 to 2 to 4 orbital resonance. This resonance prevents Europa's orbit from circularizing, constantly nudging it back into that imperfect ellipse. As Europa moves along this elliptical path, it alternately approaches and recedes from Jupiter. And Jupiter's gravity, the most powerful gravitational field in the solar system aside from the Sun itself, responds to this changing distance by constantly squeezing and stretching Europa's interior. The closer Europa gets, the stronger the pull. The farther it swings out, the pull relaxes. Back and forth, squeeze and release. Over and over, for billions of years. This is called tidal heating. It is the same mechanism that makes Io the most volcanically active body in the entire solar system. Io is so violently kneaded by Jupiter that its surface is covered in erupting volcanoes and lava lakes. Europa experiences a gentler version of this same process. But gentle, in this context, is relative. The energy deposited by tidal heating into Europa's interior is enormous by any earthly standard, and it has been running continuously for the entire history of the solar system. Imagine squeezing a rubber ball rapidly in your fist. You can feel it warm up within seconds. Now imagine that ball is 3,100 kilometers across, and the hand squeezing it belongs to the most massive planet in the solar system. The heat generated by that deformation doesn't just warm the rock, it keeps an ocean of liquid water from freezing. It may drive hydrothermal systems on the ocean floor. It may power chemistry that, on Earth, gave rise to the first life nearly 4 billion years ago. The ocean that this heat maintains is estimated to be between 60 and 150 kilometers deep. Let that settle in for a moment. The deepest point in Earth's oceans, the Challenger, deep in the Mariana Trench, reaches approximately 11 kilometers. Europa's ocean may be more than 10 times deeper than that, and this entire ocean is contained within a moon smaller than our own moon, wrapped in a shell of ice, orbiting a planet that would destroy any unprotected human within hours. At the bottom of this water column lies a rocky, silicate seafloor. Not a layer of high-pressure ice, as you might find in the deep interiors of larger moons like Ganymede. Actual rock. This is critically important. Rock-water contact is where mineral chemistry happens. It's where hydrothermal vents could form, where hot mineral-laden water could mix with cold, oxygen-rich ocean water, where the kinds of chemical gradients that power early microbial life could exist. On Earth, hydrothermal vent systems at the ocean floor are teeming with life. Vast ecosystems of microbes, tube worms, shrimp, all living in complete darkness, fed entirely by chemical energy extracted from the rock. If such systems exist on Europa's floor, they could, in principle, do the same. Webb's carbon dioxide discovery fits into this picture with almost unsettling precision. If the ocean floor is hydrothermally active, and the ocean contains dissolved carbon, and the system has been running for billions of years, then Europa possesses 3 of the 4 ingredients typically considered necessary for life: liquid water, a chemical energy source, and organic chemistry. The 4th ingredient is time, and Europa has had time in abundance. This is not to say that life is there. Let me be absolutely clear about that. The discovery of carbon dioxide on the surface of an icy moon is not the same as finding a microbe. The gap between conditions that could support life and conditions that actually produced life is enormous. We have exactly one data point on how life originates: Earth. And drawing sweeping conclusions from a sample size of 1 is not science. It is wishful thinking, however thrilling the data may be. What Webb has done is narrowed the list of reasons why life on Europa would be impossible. Before these observations, Europa had confirmed water and confirmed energy. Now, thanks to Webb, it also has confirmed carbon. Every verified ingredient reduces the number of excuses for life not to exist there. That is not the same as proof, but it is progress of the most fundamental kind. There is another piece of the Webb data that has received less attention than it deserves. Both research teams were also actively searching for complex organic molecules. Sophisticated carbon-based compounds, the kind that serve as the building blocks of biological chemistry. Amino acids, lipids, long-chain hydrocarbons, the molecular vocabulary of life. The results were inconclusive. Webb detected hints, spectral signatures that overlapped with complex organics. But the overlap with other simpler compounds made definitive identification impossible at this distance. The instruments were not quite sensitive enough to distinguish signal from noise for molecules that complex, on a surface that far away. Here is the thing about scientific inconclusiveness. It is misunderstood. When a researcher says, "We detected hints but cannot confirm," the public often reads that as, "We found nothing." That is exactly wrong. Finding hints of complex organic signatures on the surface of Europa, even ambiguous ones, is not nothing. It is a constraint. It says, the signal exists at or near the detection threshold, which means the molecules, if present, are not impossibly rare. It means a more sensitive instrument pointed at the same region has a realistic chance of finding something definitive. Think about how science actually moves. The first detection of an exoplanet atmosphere came through exactly this kind of edge of sensitivity measurement. The first tentative spectral hints that water vapor existed in an exoplanet's atmosphere were dismissed by some and cautiously accepted by others. Then, better instruments confirmed it. And now we routinely characterize the atmospheric chemistry of worlds hundreds of light years away. Europa's organic hints may be sitting at exactly that threshold. the place where the next instrument generation crosses from inconclusive into confirmed. But here is the crucial point. This ambiguity is not a failure. It is a targeting system. It tells the next generation of instruments exactly what to look for and exactly where to look. And the next generation of instruments is already on its way. In October of 2024, NASA launched the Europa Clipper spacecraft, carrying the most sophisticated instrument suite ever sent to the outer solar system. Clipper will conduct approximately 50 close flybys of Europa over the course of its mission, some passing as close as 25 kilometers from the surface. It will map the ice shell in detail, measure its thickness and internal structure, hunt for active plumes and analyze whatever they eject, probe the ocean's depth and salinity using radar and magnetometry, and taste individual particles of ice and dust with instruments sensitive enough to detect organic compounds at parts per trillion concentrations. Clipper's arrival at Jupiter is expected in 2030, but the Webb observations have already sharpened its scientific targeting. Terra Regio, once simply a region of geological interest, is now a primary mission focus. The disrupted terrain, the carbon signature, the geological youth of the surface. These are the markers of a place where the ocean is actively communicating with the exterior. Clipper will listen to that communication up close. But Clipper must operate quickly when it does, because the environment around Europa is not forgiving. Jupiter's radiation belts bombard Europa's surface with up to 540 rem per day, a dose that would kill an unprotected human within hours. It is an invisible, relentless storm of charged particles accelerated to near-light speeds by Jupiter's enormous magnetic field. To give you a sense of scale, the radiation dose at Europa's surface is roughly equivalent to receiving more than 5,000 chest X-rays in a single day. The annual occupational dose limit for nuclear power plant workers in the United States is 5 rem. Europa receives over 500 rem every 24 hours. There is no biological adaptation that could keep a human alive in that environment. A week on Europa's surface, even inside a heavy radiation suit, would be a death sentence. Clipper's sensitive electronics are protected inside a titanium radiation vault with walls nearly a centimeter thick. Even so, engineers estimate that the cumulative radiation exposure over the mission's 50 flybys will degrade the spacecraft's electronics to near the limit of operability. This is a machine being deliberately sent into an environment that is slowly killing it, making as many observations as possible before it succumbs. But even this shielding only permits short passes near Europa. The spacecraft must repeatedly retreat to safer distances before the radiation destroys its systems. This is why 50 flybys were planned instead of a stable orbit. A spacecraft orbiting Europa would have its instruments fried within weeks. This radiation is also one of the most fascinating and counterintuitive aspects of Europa's story. On the surface, Jupiter's radiation is sterilizing. Any complex organic molecules that make it to the surface, carried up from the ocean through geological processes, are destroyed within decades. The radiation tears apart molecular bonds, scrambles amino acids, reduces whatever chemistry the ocean produces into simple inorganic fragments. If biosignatures are rising from below, they are being erased almost as fast as they arrive. This is one of the reasons Clipper will need to catch fresh material as quickly as possible after it is exposed. But follow the radiation deeper. As it strikes Europa's icy surface, it splits water ice into its constituent atoms, hydrogen and oxygen. These radiolytic products then recombine in novel ways, generating compounds like hydrogen peroxide and molecular oxygen. Some models suggest that this radiolytically produced oxygen can gradually migrate downward through the ice, eventually reaching the subsurface ocean. Once in the ocean, this oxygen could serve as a powerful chemical oxidant, a source of chemical energy that could fuel metabolic processes in any organisms that happen to be there. Think about the elegant, savage irony of this. Jupiter irradiates its moon with levels of radiation that would kill every known form of complex life on Earth. That same radiation, modified by its journey through kilometers of ice, may be generating the very chemical fuel that powers life in the ocean below. The destroyer becomes the provider. The poison becomes the energy source. Europa does not follow our intuitive rules. There is yet another layer to this story that does not appear in most headlines. Toward the end of 2024, new web observations revealed crystalline water ice structures on Europa's surface that appeared unusually fresh, ice that had not been significantly processed by radiation. In the context of a moon constantly bombarded by Jupiter's particle storms, fresh ice is a significant marker. It means the surface is being renewed. Material from below is pushing up, displacing the heavily irradiated upper layer and replacing it with new, unprocessed material from the interior. The distribution of this fresh ice coincides precisely with the same disrupted terrain regions where the carbon dioxide had been found. The same areas, same coordinates. This is not coincidence. It is confirmation that the processes happening beneath Europa's surface are active and ongoing, not ancient, not historical, but current. The chemistry Webb detected is not a frozen record of something that happened billions of years ago. It is a live dispatch, a present tense signal. When scientists examined the spectral data more closely, they found something else. The carbon dioxide was mixed with salts, specifically sodium chloride and magnesium sulfate, table salt and Epsom salt, ordinary, mundane, deeply familiar compounds, and also, coincidentally, precisely the kinds of salts dissolved in Earth's oceans. Their co-occurrence with carbon dioxide in the same geologically active regions paints a picture of a tightly coupled system. The ocean is not just leaking carbon upward. It is communicating its full chemical character, salts, gases, dissolved compounds, through the ice, up to the surface, where Webb's instruments can read it like a letter slipped under a door. The surface is a messenger board for the ocean below. And Webb is the first instrument sensitive enough to actually read the messages. The salt composition also carries deep information about the ocean's habitability. On Earth, hydrothermal vents release characteristic mineral ratios that depend on the temperature of the vent fluids and the composition of the surrounding rock. If Clipper can precisely measure the salt ratios on Europa's surface and match them against tidal heating models, scientists may be able to estimate the temperature and chemistry of the ocean floor, without ever going there. It would be like reading someone's diary by analyzing the chemistry of the ink without opening the cover. Meanwhile, another spacecraft is traveling more slowly toward the same destination. In April of 2023, the European Space Agency launched JUICE, the Jupiter Icy Moons Explorer. JUICE is primarily focused on Ganymede, the largest moon in the solar system, which also harbors a subsurface ocean. But JUICE will conduct 2 flybys of Europa, and its instruments complement Clipper's in important ways. Between the 2 missions, scientists will be able to cross-check data, identify systematic errors, and triangulate measurements in ways that single-mission science cannot achieve. In planetary science, redundancy is not waste. It is how you avoid the ambiguity that haunted Hubble's plume detections for nearly a decade. Now let us talk about the deeper layer of this story, the one that goes beyond the chemistry and the instruments and the orbital mechanics. For most of human history, the question of whether life exists beyond Earth was theological. It was a matter of philosophy, of faith, of metaphysical speculation dressed in scientific clothing. We could debate it endlessly, but we could not test it. We could not design an experiment to answer it. The question had no empirical handle to grip. Then we built telescopes and sent spacecraft, and walked on the moon, and landed rovers on Mars. We mapped Venus and found a furnace. We cataloged the outer planet moons and found them largely scarred, airless rocks. Slowly, without any formal announcement, the question shifted. Not from, "Is there life out there?" but from, "Is there life?" to, "Are there ingredients?" Because the second question has an answer you can find with a spectrograph, and that is exactly what Webb is doing. Terra Regio has become, in a very real sense, the geographic center of this entire inquiry. This geologically young, constantly churning, internally pressured region of Europa's surface is not just an interesting feature on a map. It is the place where the ocean speaks, where upwelling material punches through the ice and briefly contacts the surface before being battered by radiation. It is a readout of the ocean's internal state, written in carbon and salt and fresh ice. If a future mission ever drills through Europa's ice, Terra Regio will be among the first candidates for a landing site. Webb has placed a large X on the map, not metaphorically, literally. The chemical signature concentrated in this region represents the best current guess for where the ocean is closest to being accessible. Now close your eyes for a moment and imagine standing on Europa's surface. The first thing you notice is the silence. Not just quiet, absolute silence. There is no wind because there is no atmosphere worth speaking of. The pressure at Europa's surface is essentially zero. Nothing moves, nothing sounds. The only sensation is the faint vibration of ice beneath your boots, the subtle trembling of tidal flexing, the slow rhythm of the moon being squeezed and released by a force you can't see. The ice beneath you is not white. Up close, it is yellowish, tinged with the reddish-brown of the lineae, the radiation-processed salts and organics that streak across the surface. You are standing on chemistry made visible. Every discoloration is a record of a process. Every ridge is a scar from a tidal event that lasted thousands of years. The cold is not like any cold on Earth. At -160 degrees Celsius, your suit's heating system is fighting a thermal battle every second. Metal becomes brittle, lubricants freeze, unprotected electronics fail in minutes. The Apollo astronauts on the moon dealt with temperature swings from 120 degrees in sunlight to -170 in shadow. But they were only a few light seconds from home. You are 43 light minutes from Earth. A round-trip communication with mission control takes an hour and a half minimum. If something goes wrong, there is no help coming. Not soon. Not fast enough. Then you look up. Jupiter fills the sky in a way that no photograph can prepare you for. It spans approximately 24 degrees of arc, 48 times larger in apparent diameter than the full moon appears from Earth. It is not a disk. It is a wall, an orange and cream and brown wall of roiling clouds, banded with storm systems larger than Earth, anchored by the Great Red Spot. A storm that has persisted for hundreds of years, a bruise that never heals, drifting slowly across the planet's face like a slow sigh of geological violence. You can see its rotation in real time. The cloud bands slide past each other at different speeds, shearing, curling into eddies, merging and separating. It is not static. It breathes. You realize, standing there, how completely Europa belongs to this planet. The tidal forces keeping the ocean liquid come from Jupiter. The radiation sterilizing the surface comes from Jupiter. The gravitational resonance locking Europa's orbit comes from Jupiter's relationships with its other moons. Europa does not exist independently. It is a creation of the gas giant looming above you, sustained by it, defined by it, endangered by it, and perhaps, made habitable by the very forces that make its surface lethal. The paradox at Europa's heart is this. The same moon that harbors one of the most promising candidates for life in the solar system has a surface that would kill a human being in under a day. The radiation dose at Europa's equator is roughly 5,400 millisieverts per day, the equivalent of receiving more than 5,000 chest X-rays in 24 hours. the upper body's DNA would be shredded. Cell death would outrun the body's repair mechanisms within hours. And yet 10 kilometers below your feet, in darkness and pressure and warmth, something might be swimming. Let us now talk about what all of this actually changes, scientifically and in terms of what we believe. Before the Webb observations of September 2023, Europa was a promising candidate. It had water. It had energy. Scientists were optimistic, but operating largely on plausibility arguments and aging Galileo data. The carbon detection was hypothesized but unconfirmed. The ocean's chemistry was completely unknown from direct observation. Europa was a hope more than a target. After Webb, it is a target. A concrete, specific, chemically characterized target. The carbon dioxide detection confirmed that the ocean contains dissolved carbon. The salt identification suggested a chemistry not entirely unlike Earth's oceans. The fresh ice distribution told us the internal geology is active right now. The plume constraints told us how to interpret future detections and where to look. And Webb's hints at complex organic signatures, even inconclusive ones, gave Clipper a precise chemical shopping list. We now have testable hypotheses, specific predictions about what Clipper should find in Terra Regio when it passes 25 kilometers above the surface in the early 2030s. We have a region, a composition profile, a list of target molecules, and a geological framework. The transformation from interesting moon to live scientific investigation is complete. And when Clipper arrives, when it makes its first close pass, when Suda catches a grain of ice the size of a grain of sand and runs it through a mass spectrometer, when Reason's radar pulses penetrate 30 kilometers of ice looking for liquid pockets, when the magnetometer measures the ocean's depth and salinity, we will know things about this ocean that no human has ever known about any body of water beyond Earth. Here is what would happen if, somewhere in all that data, we found the signal we are most afraid to hope for. An amino acid profile that doesn't match anything produced by abiotic chemistry. A lipid signature suggesting membrane chemistry. A molecular pattern that on Earth would be produced only by life. That discovery, not a confirmed organism, not a moving creature, not anything we could photograph, just a set of molecules in the right configuration, would be, without any exaggeration, the most significant scientific discovery in the history of humanity. Not because it would prove life on Europa, it wouldn't, not definitively, not immediately, but because it would prove something larger. That the chemistry of life is not unique to Earth. That the universe assembles these molecules wherever conditions allow. That we are not a miracle, we are a pattern, replicated wherever physics permits. We are not there yet, we are nowhere near there. But for the first time, we are not simply hoping and theorizing. We have data, we have a target, we have instruments en route. Europa was never trying to attract our attention. It made no spectacle of itself. While Enceladus was erupting geysers visibly into space, and Titan was showing off its orange haze and exotic chemistry, Europa just sat there, white, cracked, quiet, hiding an ocean twice the volume of all Earth's water under 30 kilometers of ice, sealing its secrets behind a surface that radiation would scour clean within decades. 2 decades of tantalizing, insufficient data. 2 decades of pressed faces against frosted glass. And then Webb looked carefully and patiently and read what the surface was saying. The ice has not yielded yet. It has not broken open. But Europa Clipper will pass closer to this world than any spacecraft before it. Its SUDA instrument will catch particles the size of dust and read them like telegrams from the deep ocean. Its radar will scan the ice layer by layer, looking for pockets of liquid water that might be trapped just kilometers below the surface. Water that could be more accessible to a future lander than the deep ocean floor. Those shallow liquid pockets, if they exist, change the geometry of exploration entirely. The deep ocean is 60 to 150 kilometers beneath the surface, a drilling challenge so enormous it defies current technology. But if water pools exist within 10 to 15 kilometers of the surface, in the lens-like reservoirs that the chaotic terrain models predict, then the target becomes reachable. The horizon moves closer, and the chaotic terrain itself, the jumbled, refrozen, tilted ice blocks that cover roughly a quarter of Europa's surface, may be the geological signature of exactly this process. Warm material rising from below, softening the ice, destabilizing the surface layer, which collapses and refreezes in angular disorder. If Clipper's Reason radar confirms liquid water in those zones, it won't just tell us where the water is. It will tell us that Europa's interior is in active geological conversation with its surface, that the system is alive in the most literal geophysical sense. Somewhere in the contradiction between a surface that destroys organic chemistry and an ocean that might generate it, the oldest question in science is waiting to be answered. The question of whether we are alone. The question of whether the universe makes life wherever it can, or whether Earth was a singular, unrepeatable accident. We do not know the answer. We should not pretend we do. But for the first time in the history of astronomy, we have a specific place, a specific chemical composition, a specific mission with specific instruments, and a specific window of time, the early 2030s, in which we might take a meaningful step toward finding out. What would we do with a sample of Europa's ocean water in a laboratory? Not a composition inferred from orbital data, not a model extrapolated from surface salts. An actual sample, a test tube of water that has never seen sunlight, drawn from an ocean that has been sealed beneath ice for billions of years. If that water contained amino acids, the building blocks of proteins, in ratios that could not be explained by abiotic chemistry, the scientific world would transform overnight. If it contained lipid-like molecules consistent with membrane formation, with the kind of self-organizing chemistry that precedes cellular life, even the most cautious scientists would be unable to avoid the conclusion that the universe builds toward biology whenever conditions allow. That would not be evidence of life on Europa. It would be evidence of something larger, that the chemistry of life is a natural consequence of the universe's laws, not a once-in-a-universe accident. And if, far further down the road, perhaps in the 2040s or 2050s, when the technology to drill through kilometers of ice has been developed and tested and refined, a lander actually penetrates the shell and lowers instruments into that water, the results could be revolutionary in ways that are genuinely impossible to fully predict from here. Because we have never encountered another body of liquid water anywhere in the universe. We have never tested whether the origin of life is reproducible. We have no way of knowing, right now, whether we are typical or anomalous. Europa might tell us. This is what a telescope the size of a tennis court, orbiting 1.5 million kilometers from Earth, looking at a moon 600 million kilometers away, has given us. Not an answer, but the specific shape of the question, the chemical outline of a target. The first real evidence that the ocean of Europa is not just wet, it is rich and active and chemically complex, and may have been so for longer than life has existed on Earth. We are standing at the edge of something that does not yet have a name. The data is real. The missions are flying. The instruments are pointed. And the next chapter of this story will be written not in speculation, but in measurements. The ice has not opened yet. But we have the tools to listen to what it is whispering. And for the first time, what we are hearing is not silence. I hope you enjoyed the video. If you did, please leave a like. It genuinely helps this channel reach more people who love stories like this one. And subscribe if you haven't already, so you don't miss the next chapter of this extraordinary cosmic saga. Thank you for being here. I'll see you in the next one.